An important tool in dealing with waves is the equation that relates the tension in a string or rope or any linear medium to the mass per unit length to the speed of propagation of the wave. Thinking of the bead, the less mass you have, the more quickly the bead is going to accelerate. So if there's less mass and less mass per unit length, that's going to give you a greater propagation velocity. Everything's going to happen more quickly simply by Newton's second law. You're going to get more acceleration and a quicker change in the position of each bead, the less mass per unit length you have. And of course, if you have more tension, that gives you more force. That net force, the force we got, the 2 Newton and the 1 Newton force, if you double the tension, that becomes a 4 Newton or a 1 Newton force. If it's on the same mass, it's going to accelerate things faster. So less mass, more tension gives you quicker propagation. Now that's not a derivation of this particular explicit formula. It doesn't explain why this is a square root here, why you have a square root of both. But it does explain why t should be in the numerator and mu in the denominator. Now, as an example, we could actually calculate for that model, for that bead model, if the mass per unit length is 5 grams and you have a 10 centimeter spacing of the bead, that means you have 5 grams every 10 centimeters, so your mass per unit length is 5 grams per 10 centimeters, which becomes 0.05 kilograms per meter. Unless I did something really ignorant here, you better check me on that. Okay, we had a tension, postulated a tension of 10 newtons. So what do we have? We have C equals a square root of 10 newtons over 0.05 kilograms per meter. That's about 14 meters per second. If you work out the units, you'll find that you have meters squared in the numerator and seconds squared in the denominator under the square root, and that's going to end up with your meter per second unit. Okay? Now, this isn't relevant to this. We'll talk about that in a minute. Okay. Another example. Sorry, I was kind of distracted by some loud noise in the hall there, just making sure that there's no violence going on. Okay. I'd hate to have to intervene for my own sake as much as anybody's. Okay, propagation speed for let's say the question in the set of problems. Might have to close that door, but it's office hours. Okay, I'm gonna do something. It turns out that was actually one of my former students. Good student, good guy, big guy. Glad I didn't have to intervene with him. Okay, I don't do that to all my students. So. And in other words, you're probably not going to end up in the hall making that kind of noise, having been a student. Okay, well, we have a 10 meter string, 20 grams, 4 newtons. This is in the document that we're talking about. So this is the question that was posed. Okay, and we do the same calculation. We have 20 grams in 10 meters is 2 grams per meter, which is 0.002 kilograms per meter. The units then work out to meters per second, and I believe this is going to be the square root of 2,000 meters squared per second squared. That gives you something close to 45 meters per second. Okay. Now, next question. If you have 30 cycles per second, and you need to pause and do this. This is very straightforward, but now we're going to apply it. At 30 cycles per second. Now this means, for example, the left end of the string is oscillating at 30 cycles per second. Now, those oscillations are going to propagate down the string. So if you have 30 cycles per second, how far is it going to be between the peaks? You should work that out before you look at my solution or listen to it, okay? Well, there are various ways to reason this out. One way is, 30 cycles produce 30 peaks. And it takes a second to do that. In that second, those peaks are going to get spread over the 45 meter distance that the wave propagates in a second. with the result that the distance between the peaks has got to be 45 meters over 30, or 1.5 meters. You can have a picture, 30 peaks. You can draw 30 peaks, just draw a wavy line with 30 peaks in it. Visually, that's going to represent 1 second, and it's going to represent a span of 45 meters, so it's going to be clear that the distance between the peaks has to be 1.5 meters. Another way to get the same result, ask the question, how far does a peak propagate in 1/30th of a second? You have a peak every 30th of a second, so between this peak and this peak, how far has the wave propagated? Well, it's propagating at 45 meters per second. In a 30th of a second, it'll propagate 1/30th of 45 meters. 1/30th of a second times 45 meters per second gives you 1.5 meters.